Hey class, today we're going to go over the Collatz problem and numerical integration, and if we have time we'll discuss AVL trees and binary search trees, and if not then we will deal with those next time. Okay, so the Collatz problem is a recursive function, but a conditional recursive function. So we continue to call the same function, passing in the previous term, and we execute one branch if it's even, and then the other one if it's odd, and then we take the output of it and we pass it in here. And if the sequence ever reaches a term which is 1, then we halt the sequence, and the sequence from your initial choice to all of its successive terms becomes the solution, or the proof that there is that given that particular number the sequence halts. So we would like to demonstrate that this sequence for any choice, any positive value of a sub 0, so any initial choice which is a positive integer, is going to yield, is going to eventually yield to a finite sequence following these rules. So it's deterministic. So there's nothing that can really happen. It's just a question of whether or not for every positive integer that the sequence terminates, or whether or not there's some loop. And so there is a trivial loop. If we plug in, if we choose a sub 0 is equal to 1, 2, or 4, then we'll enter into this loop. So if it's on, if your initial choice is on, then you execute the odd branch, right? So 3 times 1 is 3, plus 1 is 1, so we get 4. This is even, so we cut it in half. And this is even, so we cut it in half. And so if you start with 1, then you get the full cycle. If you start with 4, then you just cut it in half. If you start with 2, you cut it in half, and you terminate with 1 eventually. But you're back to your initial choice, and so you'll just continue in that loop. And so the result that we hope to demonstrate is that this is the only such loop. Everything else terminates whenever you get to a 1, and then of course you enter into this loop if you continue past it. Okay, so with that in mind, let's switch over to the text, and then we'll discuss it, we'll write code where applicable, and then we'll move on to numerical integration. Okay, so we spent that time discussing Collatz, and we know that we want to show that the sequence halts, that the sequence always halts. And so we'll begin by straight away defining an alternative sequence. So in the sequence that we had, we executed one condition if it was odd, and another if it was even. But it's unwieldy to have those branches. It's really difficult to make statements using limits and so forth whenever you have to continue to choose. You have to choose this execution path. So it's more desirable if we can unroll it. Now, if you're broadly aware of the topic of compiler design, then one of the choices that a compiler has to make, or the platform executing it, is how far in advance to execute or to anticipate that a loop will execute. So you're given a loop and you're trying to streamline the actions, so you queue up all of the subsequent actions. So it's additional work for the program, or the program adds additional work to the processor if it has to lay out the plan for the loop every time. And so one of the optimizations that gets made is that the compiler will anticipate some multiple of 8 iterations per loop. And so if it's wrong and it overestimates, the cost isn't too heavy, and if it's greater than 8, then it was a reasonable hedge. It was a reasonable protection against too much tax on the processor, and so you got decent gains out of it. And so we want to do something similar here. We want to unroll the execution of events so that they happen in this unidirectional fashion. So rather than having the number bounce up and down, we want to construct this alternative sequence which only increases. But we want to devise it in a way that's compatible with what we're already dealing with. So this is entirely new notation, this sigma, and you pass it in the previous term, right? So this could be a n plus 1, and this could be a n, right? But here in this convention we're using the previous term, right? So sigma considers a term, right, the previous term, the input to the current function, and it returns the largest such value k, where ai divided by that power of k is a natural number. And so it's the greatest common multiple in terms of powers of 2, or it's the first, the largest proper divisor in terms of powers of 2 for the previous term. So this is very similar to what we do with bit shifting, and I want to make it clear what's going on with that. So let's jump over to our console. And so bit shifting is direct manipulation of the way we store integers. So if you remember, we just store them in terms, we can view it in terms of this base 2 expansion of the numbers, where each of the 8 bits or 64 bits or however many you're using are that the placeholder for that power of 2 in terms of significance, ranging from 0 to n minus 1, where n is the number of bits. Right? So we can represent the powers of 2 using these bit shifts. Right? So if you shift it once to the left, if you shift a1, a proper 1, well then this number is just the least significant bit. And so we're taking the binary representation of this, which is all zeros and then a 1 at the end, and then we're adding this many zeros, right? We move the 1 to the left this many places, and we fill it in with zeros. So when we do that once, we get the binary representation of 2. If we do it twice, we get 4, 3. So 2 to the 3 is 8, 2 to the 4 is 16, and so on and so forth. So we get the binary powers of 2 by doing this. So this function, the sigma function, it takes the previous term in the sequence, and it tells you what the least significant set bit is. So we're calling it sigma of a sub n. Right? So let's okay. So let's create a function, a sigma function. Right? So sigma is equal. It takes as input the previous term. And then it attempts to find this value, this most significant common divisor. Right? Okay, so we know that that all numbers in JavaScript are 64 bits, but they are floating point So it's 64 bits with floating point, which means that there's 52 significant digits. I feel like I'm using the wrong word there, but the ones that represent the number of significant digits. But we will assume, for this sake, that we're only dealing with 32-bit integers. So JavaScript it allows us to use more significance than that, and it does have an internal representation of an int that gets called whenever you do actions like this that are clearly meant to manipulate integers. But we'll just assume that's a 32-bit int. Okay, so while we don't overflow the integer, we're going to execute this loop. Let's see. So we want to know the tally, basically, how many shifts it was required in order to find this first non-zero value in our binary representation of the number. So we loop through, and then we check to see whether or not, so if a sub n with the bitwise AND operator 1 shifted to the left I times, right? So this creates a number which has exactly one non-zero value in its binary representation, and that non-zero value occurs on the ith most significant digit, where those are just powers of 2. So these are all the powers of 2. So the first one that is non-zero, right? So we have to check for non-zero. Then we can halt our loop. It will have found the value. Actually, we don't need to track it, because if we exit the loop without finding it, we return -1. Right? And if we did find it, then we return I. And so, okay, so we've created that. So let's see how it works. So we know from these inputs what it should look like. It should be this value right here. Right? So let's test it and make sure that it's producing those results. So we pass in 0, it returns -1 because it never found a non-zero value. 1, yeah, that's correct. Uh-oh. Okay. So let's execute this part and see what we did wrong. So in this case, a sub n is going to be this. And then I is going to be all of the values from 0 to 32. So we start with 0. And then that should have been true. This bitwise operation should hold. So 2 should not be equal to 0. There we go. Okay, so okay, so what was happening is it was performing this bitwise operation, and JavaScript, again, JavaScript wants to help you out. So it knew that there was a Boolean condition, right? This not equal to 0 condition here. And so the Boolean condition was occurring within an if block. So it knows that if it's going to help us out, it needs to convert everything to a Boolean value. And so it would perform this, and that would be a 2, which is non-zero, and so the truthiness of that is true. And then another 2, which is again is non-zero. So we have true and true, and this can double as both a bitwise operator and a Boolean operator. If you use it as a Boolean operator, then it fails to short circuit the test, which means that if you have a bunch of if x and y and z and so on and so forth, if you use the double ampersand, then if it's already false, if the statement's false, then it skips and it moves ahead. If you use the bitwise one, then it executes every one of those conditional checks. So there's no short circuit, there's no realizing that it's impossible and then moving forward. It attempts to go forward with all of them. So realizing that it had a Boolean operation on its hand, it did true and true, and then it did an exact comparison of type to see whether or not true not equal to 0, right? And so it's true, but I mean, let's test that out. Well, it still should have come across true. So it's obviously I could speculate as to what I think happened, but I'm not sure that I'm going to come up with a good answer. In short, we need to wrap this though in a set of parentheses, and that'll ensure that it executes this, and that the output is an integer rather than whatever was happening before. Alright, we've already created a variable in this scope, so we get rid of the let variable declaration. Okay. So now let's test. Zero, good. 1, good. 2, 3, and that's weird. 3 should really return 1 because it's an odd number and the 1 is set. So again, maybe this is an instance where, because we don't have true types or full control over it, perhaps it's made more confusing by the attempt to use JavaScript. But we'll move forward without it. I can use the whiteboard, but yeah, we'll move forward without it. Okay, but that's the spirit of what we're trying to do here. We're tracking these, whether or not the first set bit when coming from the right. And so this is growing all the time. In the Collatz sequence, whenever we multiplied by 3, we added 1. And so we always got an even number after we did something like this. And here, we're multiplying by 3, and then we're adding the least 1, right? The least significant bit gets added again. It's at its somewhere between multiplying by 3 and multiplying by 4, right? And that'll come up again. Okay, so we have this concept of something which tracks that least significant set bit. Okay, so then this 2 to that value, whatever the exponent for the power of 2, which is the least significant set bit, right? And so if we were dealing with decimal, then this would be the equivalent of saying, if you add the number 100,200, then in base 10, the hundreds would be the least significant set decimal value, the least significant non-zero decimal value. And so we're tracking the equivalent of that. So then this is like saying the hundreds place, or the 256's place, or the 65,536's place, whatever the value of this is. And so we're going to call it the sweeper term because in the end, as you'll see, it comes along and it just sort of scoots those bits along. It gets them moving, and it increases the trailing bits so that they kind of all roll forward, and then you get this convergence towards a power of 2. And so we call it the sweeper because it acts like that. And then right, and this is the polynomial view of it that we were discussing before. So now we're going to define this alternative series, B sub n. So B sub n is really just 4 times the previous term, but if you apply it repeatedly, then you end up where the nth term in this sequence is being 4 to the n times whatever that initial value was. Okay, so if we begin with the term a sub 0 equals 1, as we demonstrated, then we see the effect of the sweeper term, right? Times 3 plus 1, it's 4 to the 1. Hey, this is exactly the same as the term in our B sub n series, which is 4 to the n times the initial value. Well, if you start with 1, then these two values are equivalent. And in fact, they're equivalent after a second iteration, whenever we apply it again. So before we began our loop and we started dividing by 2, but here it's strictly increasing. Okay? But we're increasing it in 2 different ways. So in the B sequence, we're increasing it by exponentiation. We're just multiplying by 4 each time we visit it. So it's just 4 to the n, right, every time. In the A series, we're increasing it by taking a look at its value, and then we multiply by 3, and then we add 1 more of whatever that least significant bit was. But if it's a power of 2, then there's only 1 non-zero bit. And so this value turns out to be exactly the same as this value because it's a power of 2. So then this becomes the equivalent to multiplying by 4. Right? And so that's the case whenever you start with 1. Right? But it's a little bit different for other cases. But we'll show that this is significant because we're going to use this to force convergence. We're going to use the fact that once you have a power of 2, that it grows at the same pace as 4 to the n later. So we make a note of it here, right? So it's maximal. It grows the most whenever the least significant bit is as significant as possible. That makes sense. Right? Okay. And then just a note on how this looks in terms of the binary representation. So 3 times a sub n minus 1 plus our sweeper term is going to look like this, right? So you have the kth coefficient, and it's times 2 to the k, and so on. But we multiply it by 3, right? So we end up with one of these, and then everywhere else, except for that final term, we're adding adjacent values, essentially. This might be easier. Well, we'll just run through it. It's fine. Okay, so this is a view of the binary number, but don't worry about it too much, right? So the trick is really going to be in showing that once it converges to a power of 2, it grows at the same as 4 to the n. But if it helps to view this and review multiplication by 3 in binary, where it's multiplication by 2 plus a number which is exactly the same as the original number, right? So 2 plus 1 is 3. So so we could break it up like that. And so multiplication by 2 in binary is really easy because you shift it to the left. And then addition is really just adding the two numbers together. It's no special trick there. And so this is why you get these adjacent numbers all added together. Because when you shift it to the left, then this one is now being added to this one, which was shifted over by 1. And those become the value for the kth entry. Okay. So we say in the case of a power of 2, then the right-hand side looks like this. Right? So the least significant bit is 2 to the k because it's a power of 2. Right? 2 to the k plus 1 has a 1 because whenever we're multiplying by 3, again, we shift to the left 1, so that's what we see here. And then we add it to the original value, which is what we see here. So this is 2 plus 1, right, plus our sweeper term. Well, it was a power of 2, so there was only one non-zero value. Right? So these are going to have the same value. And 2 of these makes 1 of these. So there's really 2 of these. But 2 of these makes 1 of these, right? Because we're dealing with powers of 2. So each time you get a 2, you increase the to the next place. Right? So this is the same as multiplication by 4. Okay. So to arrive at the contradiction, which proves the result that we're trying to demonstrate, then let's assume that they don't converge, that there is some counterexample, some other non-trivial loop, which doesn't converge to a power of 2. Right? So this would be a condition, because once we converge to a power of 2, well, the Collatz sequence would just have us divide by 2 until we get all the way back to 1. Like, we haven't done anything different except that we no longer divide by 2, but we're still adding the growth term in the same fashion. Right? To say that there's some loop out there is equivalent to saying that you have some infinite sequence which never converges to a power of 2. So let's assume that that's the case. Right? So then we give the binary representation, but this might be more confusing than it is helpful. And so now we say, okay, well, we know that the sequence grows at its fastest whenever the sweeper term is adding the most significant bit of a number, which is only the case whenever it's a power of 2. So then what can we say as to a lower bound for that sweeper term, for the value which we add whenever we grow the number for the next term in the sequence? If it never converges, right, then we know that it's not equal to the most significant bit, and we know that it will never be equal to that because that's only the case when it's a power of 2. So then the largest term that we can have, the largest value for a sweeper term, is the one next to that most significant bit. So if we just consider the second most significant, or the most significant bit divided by 2, then we get this value, right? But that's not the whole number, a sub n minus 1 divided by 2. It's just the most significant bit divided by 2, right? So that we can consider something that is larger, or as large as possible for this. So let's say we just keep adding this over and over again. Okay. So then that's equal to half the value of the most significant bit. Right? So we can see it in binary if we care to do so. And we're adding it over here, so this is the sweeper term, and then that corresponds to really this one over here. Right? So then this series, this one that we're constructing now, which never converges to a power of 2, so it is the contradiction to the Collatz Theorem, and it is bounded above by a sequence which grows at this rate, where we're always adding that second most significant bit. Okay, well here we're only adding one non-zero value, and it's equal to half the most significant bit divided by 2. But this value is itself bounded above by this value. Well, where we've discovered this by creating an upper bound for this. So now this, right, is just this one value here, and it's our upper bound for our sequence, which never converges. And so because we're adding other junk, basically, other non-zero positive value junk, we can make it grow faster, and we can do that by just dividing that original number by 2. So that is actually larger than just dividing that most significant bit by 2. Okay, so, or it's at least as large as, right? Greater than or equal to. Okay, so now we give a new name to this sequence. Okay. We've defined it as this. So it's 3 times the previous value plus half again. Right? Well, that's just 3.5 times the previous value. But that's 3.5 to the n times the initial value. But we've already explained that this is a sequence which grows, which outgrows something which grows at the rate of 4 to the n. Right? So we said that it never converges to a power of 2, and once it reaches the power of 2, it grows at 4 to the n. And we said, and we picked an initial value which is greater than 1. So the sequence has to, by its construction, by the fact that we can use the same growth function for both 1 and our power, for both the initial value of 1 and our whatever initial value is for the infinite sequence, which never converges in our perspective loop. So we're growing them using the same function, and this one supposedly outgrows it, but we're growing it by the same method, so we're always adding values which are smaller than this, but then we end up with a sequence which outgrows values which grow in that fashion, right? And so this contradiction, the fact that it's not possible for that to happen, so for the sequence to never converge to a power of 2, and because of that, right, we see that it has to. It can't grow at something slower than 3.5 to the n, because it has to outpace that initial sequence where we chose the initial value of 1, so where we start off as small as possible, because that will eventually overtake it, and we used various bounding techniques to ensure that that couldn't happen, right? So there was a contradiction somewhere, and the contradiction was the fact that that this even exists, that there is a sequence which does not converge to a power of 2 when using these methods. Okay, so we have our contradiction, and now we say, okay, well, we've really gone out of our way to construct this function that allows us to use limits and consider this only in one direction. But we can recover the Collatz sequence by changing it back to something like this. We create this third sequence where our sweeper term is always 1. Right? So we just divide by 2 until we get back to something which is odd, and our sweeper term has a value of 1. Okay, well, now that we've done that, now that we've constructed this, it's pretty easy to relate the two. And so we see that that the way that we demonstrated the result allows us to see that this sequence, right, the one which can't exist, the one that grows forever, is eventually overtaken by this one, the one in which we began with 1 and then we just essentially multiplied by 4 with each successive term. And so there's a point where this overtakes this. Right? So this is larger for a time, and then at some point it's no longer larger than this. It becomes less than or equal to 1. So when that happens, whenever that crossover happens and this overtakes it, we know that this must have converged to a power of 2. Otherwise we would have that logical contradiction we discussed earlier. So this gives us an upper bound on how long it takes for that to happen. Okay, so we can solve for n using this formula. And then that tells us how long it takes for the sequence to overtake. And then we would have some number of zeros to delete, essentially, of insignificant zeros to the right of our 1, which represents the power of 2. And so those would be all of these terms in the Collatz sequence. So you could compute an upper bound, essentially, for... you should be able to compute a function, actually, that creates this upper bound for all of the... for when every number in the Collatz sequence has to converge. Okay, so now let's see. Okay, so now I would like to switch over to numerical integration. Okay, so before we do that, let's come back over here and discuss what it is, right? So what even is numerical integration? Okay, so if you've taken calculus and you've well, I mean, just to sit through that last part, you had to have some understanding of limits, right? And just the general feel for it. Like, is there some statement we could say that this thing does as, 2 points get close together, or, as we allow some value to run off towards the heavens? So the other questions that we would ask that are somewhat related to that are, whenever we're graphing a function or considering some function, it's going to have some behavior, and we typically want to know how quickly it's moving at a given point on the curve, right? So how it's varying as you take a step in the x direction. And so this is the derivative. This concept is the derivative, the rate of change. And that's either dy dx or y prime or y dot. There's almost certainly others. So the other question is, if we box off a region, what is the area under the curve? So then this concept is the integral. So these are the points on the line, A and B, and this is the integral under our function f of x as we vary the input x. So this is what we want to discuss today. So what is this? How do computers process this, or can they be made aware of such a concept? And the answer is yes. Right? So as with your method to approaching homeworks or proofs or exams or anywhere where you're asked to solve a problem, we return to the definition. So the definition of the integral, is given in terms of computable areas. So rather than consider the continuous area under the curve, which is what's implied by this s here, the integral, we subdivide the region and then we measure those smaller regions. And if you get small enough, then you can get away with one of several approximations, but the most common ones are going to be the rectangular approximations, which are the Riemann sums. So you just take a rectangle, height times width, and then just eventually, if you get close enough together, then it will converge. Or for an order of magnitude less error, you can use the Trapezoid Rule, where you essentially add a triangle's more accuracy to it, or remove a triangle's worth of error, depending on how you're looking at it, to your estimation with each term. And so you measure successive values, and then you take the average height, and it works out that the average height is actually so if you substitute the average height here instead of either point individually, then you get the trapezoid. And if you think about it, the area of the rectangle for the average height, like the difference between this one and this one, it's going to be halfway in between. So that kind of makes sense. But then you can also use more advanced techniques, like I think Simpson's rule. And so it's you'll go through, you'll study these things, and you'll wonder, if rectangles are so good, or if we can just use simple formula like integral of x squared dx is equal to x cubed over 3, right? And then you evaluate it. If we can just do that, why do I need to learn these additional techniques? So just in implementing the trapezoid rule, I've had to change it from something as simple as this to something where I have to measure successive points and then take their average and then multiply that by the width of the step in the direction of x. That seems like more trouble, and now you're telling me about Simpson's rule, which requires 4 or 6 measurements or whatever it is for Simpson's rule. Why bother? Why bother with that extra information? And so it's for accuracy and convergence. So you get a more accurate result quicker. You can take fewer subdivisions essentially and get a reasonably accurate result if you use something that peaks a bit further. So something like Simpson's rule, or even the trapezoid rule. Like I said, it's an order of magnitude increase in time of convergence, or decrease in terms of error, depending on how you want to look at it. And so just by taking those additional measurements, it's able to, the algorithms are able to adjust to reduce the amount of error. You get something that is a little curvier in estimate, and hence typically more accurate. And so as I guess we'll consider with these ODE methods. Um, so whenever we do numerical integration, it might be to your advantage to use something like Roncada, which is an abstraction, so something that you would use in higher dimensions, uh, and is derived from the same spirit, I believe, as Simpson's rule. So. Okay, so this is what we're discussing. I tend to favor the trapezoid rule. So if you're wondering, what it is that I'm computing instead of f of x, it's going to be the average of consecutive points. Unless my examples end up making a liar out of me, and we end up using Riemann sums. But okay, so we're discussing area under the curve, and the reason we're focusing on that is because eventually you get to a point where you're integrating values and you're continuously integrating them, but it's essentially a system of differential equations, and it kind of evolves continuously. So if you consider like the motion of planets and stuff like that, you can, I guess, sort of chart out this trajectory or whatever, but the future placement, at all times depends on your ability to track it as it's moving. So it's not an area that you're computing so much as this evolution of this dynamic object. And so that's the case, not just with the motion of planets, but in dynamical systems. So anything where you have this evolution of state where it is coming out of some sequence of previous states, and so you want to minimize the amount of error there. But we start with this because this is something that's easy to understand, and it's a remarkable result on its own. But numerical integration, which hopefully you will find to be enjoyable and fun, and most importantly of all, easy, right? So in terms of programming challenge, it's not terribly difficult. You just have to learn how to think in terms of both calculus and computer science at the same time. And we do that by returning to the definitions of what an integral is and then using that to construct a loop. Okay, so what I was going to say is we're adding each of these together, right? So we've changed this abstract notion into a summation, right? So we're now adding dx times so we have our step, right, our width, and then we have the average of two consecutive measurements, and then that becomes our area. And so adding all of those together computes the area under the curve. So let's take a look. Let's see what it's like to think of it in those terms. Okay, again, I don't know how to increase the text size. Yeah, I don't know. Okay. Alright, we've got our file. Let's switch into our directory. Perfect. Let's make sure we can do hello world. Call node. Yep, it works. Okay. So now, let's move this to the bottom. And it'll let us know whenever our code is completed. And we want an example. So the first one we're going to do is some function which depends on a parameter t. So you can think of it in terms of time, but you're going to end up using t as a parametrization a lot. So if you're comfortable with it, just think of it as the parameter t. Okay, so here we're going to define f of t as this constant c. So then if we make this substitution, then we have an integral which ranges from a to b with the constant function valued at c times the step dt, so the width of the box. And then, well, these, if you just add up this range, and it's a constant function, it's just a rectangle, right? So then it's height times width. Right? So this is the easiest thing. I mean, this is just computing the area of a rectangle. But still, we'll go through the motions, right? So let A equal 5, let B equal 10. These are arbitrary choices. Feel free to change them in yours if you care to. The number of samples that we want to take. Right? So typically whenever we run our summation, we run it from n equals 1 to infinity, or n equals 0 to infinity, or something like that. So here, I guess I should restate that. We run it from n equals 0 to the value k, or k equals 0 to the value n, whichever you're using as your indexer. And then the size, the step size dt, is your area, right? Your total width, or the length of time that you are measuring, right? So from t0 to t final, and then however many times you want to subdivide it. Well, when you divide it, you get the dt's, right? And then as you increase your number of steps, your number of samples, you decrease the step size. And so as you tend towards 0, the amount of error decreases towards 0 as well. As the step size decreases, or the number of sample increases, then the error tends to 0. Right? So it's better seeing we're just doing. So then here, which is what I was saying, your domain divided by the number of samples. We're going to use the constant value 1. Again, whenever we do summations, we initialize to the additive identity, which is 0. All integrals are essentially summations. Okay. So then this is accomplished with a loop. And we did define a function f, and it just returns the constant c, regardless of the input. But our place in time is essentially our initial value plus the number of steps we've taken times the number, or times the width of a step. And then this, the output of the function is the height, this is the width, and so our rectangle has area of this. And our approximation gets better and better as the width tends to 0. Okay, so now if we consider this as like a test case, then we have the expected value, which is just c times b minus a, an actual value, which is the summation, and an amount of error that we're willing to allow because of the way that we store decimal values in floating points. So we'll say that one part in, what is it, 16,000 is acceptable error as a result of floating point arithmetic. So we enforce that by taking the absolute value of the difference between the expected value and the actual value and seeing if that is within tolerance. Okay, and if it is, then the example 1 test passed. And if not, then we write to the error, standard error. Example 1 test failed. And then again, I always like to indicate what the expected value was and what the actual result was. Okay, let's make sure we haven't broken anything. And so it says that it passed as expected. We didn't really do a whole lot. We computed the area of a rectangle estimated by rectangles. So, okay, let's see if we can make it a little bit fancier. Okay, so now we're just using the line, right? Y equals x, or f of t equals t. And if we okay, so now our integral, we have our function f of t equals t. So then this is still, this is t. So now it's an integral of that. And then we know that the integral of t with respect to, with dt, with respect to t, is going to be t squared over 2. So t squared divided by 2, and then that's evaluated from A to B. But that's it's going to be more confusing than if we just say that it's b squared minus a squared divided by 2. Okay. So now we reinitialize our values. So a equals 0, b equals 10. Again, this is arbitrary. The number of samples. Again, we're going to use, oh, here, okay, we're only using 16 here. But we can increase it if we care to. And our function definition, that's again just the constant, or not the constant function, but the identity function. Okay, and then again we loop through. Okay, so the 0.5 is going to be this division by 2. And then here, oh, I'm sorry. So the 0.5 is for the average. So if we wanted the trapezoid rule, which I was telling you how pleased I am with its performance over the Riemann Sums. So we have this first value, and then we have the adjacent value. height. Well, that's almost the height. So we take that result and we divide it by 2. So this is the trapezoid rule, but we're still using it in this form, basically. Right? So f of t times dt. The times dt is here. The f of t, we've replaced f of t with an average of 2 adjacent points. Right? So at n and then n plus 1 to get the trapezoid rule. And so if we're satisfied with this, we can leave this here like this, or we can move the division by 2 out, or we can move it to the front as previously indicated. So that 0.5 is there for the trapezoid rule. Okay. So now we do the unit test portion of it. So we have our expected value. The actual value, which was the sum. And then the amount of tolerance. And again, 1 part in 16,000 seems acceptable. Okay, on success, we write out that we succeeded. Failure, we write to standard error that we have failed. Okay. Now we just run it. Okay, so again, our techniques have not failed us. We've been able to compute a sum, numerically integrated value for a function, which is within our tolerance of the theoretical value for such an integral. Okay, so those were really simple. We didn't really need the computer to help us along. I feel like the computer kind of took more credit than it needed to in those previous ones. But this third one really shows where numerical integration pays for itself. So now let's consider what you'll see if you take higher level differential equations. So we're going to have a vector in which we're looking for an implicit function. We're given a derivative, we're given a dynamic system, and then we are inferring the existence of some function which tells us how everything's going to behave if we sort of time evolve it, if we play it forward in time. And so this is what you'll be doing if you deal with dynamic systems. It's what you'll be doing if you deal with differential equations. So let's take a look at your possible future. Okay, so I'm giving you the syntax to create a vector in Latex. So we declare these as arrays, and I like to have my vectors with these braces around, so the array has a brace around it. The array is going to create, the vertical and the horizontal. And so here we tell it that it has just a single column. So then we'll only be creating a vertical column. So it's going to be a column vector. Okay, so we have some function which gives us the position of x at a given time, some function which gives us the position of y at a given time. But we can use these vectors to store more than that. So we have another function which gives us the value of some argument theta. So we're really going to look at a ballistics problem here. So theta is the angle with the horizon, I believe, so the launch angle, I believe. And then we have the velocity function. So we have something which accounts for speed. So the absolute value of velocity is speed. Okay, so we have our function, which is strange and exciting, and defines our system. Okay, and so now we have our derivative. And again, the derivative of a column vector is going to be, well, it's going to depend on exactly how you're differentiating it. So you might end up with Lagrangian, you might end up with the Hessian. So there are ways to consider the problem, depending on whether you have a single variable, right? You're taking the derivative of all of the functions with respect to that single variable, or if you have many positions and you're taking several derivatives, you're taking a derivative of each thing inside your original vector based on where it is in space. So you're taking a derivative for x, for y, and for z, and potentially also for theta and so forth. So depending on how you're viewing the problem, you can have either a matrix or a vector as your derivative, or possibly even a tensor if you're in the right context, right? But at its simplest, you should be able to find a way to map your system of differential equations into something as bland as this, where you have a single column vector and you just give it some generic name like either x of t or y of t. And then all of the functions, all of the position functions and arguments like this, and things that feed into the functions consumed by the derivative, live here. And then the stuff that's inside of your derivative can be computed from these values. Okay, but we'll carry on. So the derivative of our column vector is going, in this context, going to be another column vector where we've differentiated just with respect to time. Okay. And so now, the way the problem was constructed, we actually knew some of these values. So the functions in particular in the derivative. So we know dx dt, we know how it moves with respect to x. So it's going to be the speed at a given point in time times the cosine of the launch angle. Or its angle with the horizon. Okay, the change in height, change in altitude of our ballistic is going to be the speed times the sine of that angle, theta of t. The angle itself, that it makes with the horizon, is going to depend on gravity, essentially. So 9.81 meters per second divided by the speed. Times the cosine of the angle. Okay, and then the final derivative, the way that we compute the actual change in speed. So there's going to be acceleration. We're going to deal with terminal velocity in the y direction, and then we're just going to deal with drag in the x direction. Okay, so speed is updated. It's changing in negative proportion to the ratio of drag to mass. And then also in negative proportion to gravitational acceleration times the sine of our angle. Okay, and then there's a dt sitting out here. Oh wait, no, not yet. Okay, so now we've seen the derivative. What does the integral look like? Well, we've gone through a lot of trouble, so this is something fairly complicated. It's much more difficult than what we've considered above, and much more advanced. But we're given this derivative, we're given a system and a way in which it moves and how the system evolves. And we believe that there exists some function here. This is called the implicit function theorem. So if we're given a derivative and we have some parameter that we can tweak, like time, to allow the system to evolve, then we believe that even if we can't state this stuff explicitly, that there is some implicit function which represents these concepts. And so we can access it just by taking the integral of our vector here, right? Our rate of change vector. So we have some initial time and some final time. We have our vector with all of the derivatives. And so explicitly stating it, we now have this. Well, that's the same as this. And then there's that dt at the end. Okay, so how can we possibly represent this? Well, it's an array, right? Okay, so in order to consider this problem, we have constants, right, that we need to define. So there's the gravitational constant, like 9.81. And then whenever I have stuff like this, I always like to note the units in which it's measured. So meters per second squared, or variation of meters per second, right? But it's typically shorthanded to meters per second squared. So drag is unitless, but it depends on the shape as well. So, for example, parachute comes with an extremely high drag coefficient, and an Olympic diver would have a very low coefficient. Okay, so then air density. This is somewhat arbitrary. I mean, you can pick, but you want it to be realistic as well. So we'll default it to 1.19 kilograms per cubic meter. I feel like you ought to be able to convert this from air pressure and then like the average distribution of air, right? Like nitrogen is 70-something%, and oxygen and so on and so forth. So you could probably measure out the average kilograms per cubic meter if you had the pressure. Yeah, maybe. I feel like there's some way to get there through stoichiometry. But for now, anyway, we've just defined the density as mass per cubic meter. Okay, and then the cross-sectional area, well, it's area, so it's in meters squared. So what is actually exposed to the air, all of this dense air that is passing through. And then the mass itself, which we're going to estimate to be 15 kilograms. And then the initial speed, which we'll designate in meters per second. Okay, so now we need to initialize the vector. So this vector, that of our implicit function, but we definitely have implicit initial values. So then we have a launch angle, which is our initial theta. So we're going to launch it at 45 degrees. And then we're going to name our vector x sub t. So 0 there corresponds to x0 equals 0. 0 there corresponds to y0 equals 0. Our initial theta is going to correspond to our launch angle. And our initial speed was specified up here. And I guess the initial speed should technically be moved down here because it's initializing. Okay. Which is 50 meters per second. Okay. So now we initialize our integral as before. We have our beginning and our end. This is how many seconds it'll take, or how many seconds we're going to let it evolve for. Our step size, as usual, it's the domain divided by the number of samples. And then our function itself. And so okay, and so this is going to look a little weird, but it's the same as before. We just have a sampling function, which we're going to invoke. So within that function, we pull out the values, we relabel them so we remember what we're dealing with. So in this position, we're dealing with theta at x2. In this position, we're dealing with speed at x3. And then measured in newtons, kilograms times meters per second squared. So the amount of force of the drag is equal to the drag coefficient times the air density times the cross-sectional area times the speed squared divided by 2. Our dx is going to be the speed times the cosine of the angle. Our dy is going to be the speed times the sine of the angle. And the angular velocity, the radians per second, is going to be the negative of the gravitational acceleration divided by the speed times the cosine of the angle. And then our acceleration really only occurs from gravity. So it's being held back by drag, so there's a force in that direction. And then gravity is ever accelerating it downward. Okay. And so now the return of the function, and it returns the vector. So it returns our derivative vector. So dx, dy, omega, and acceleration. Okay. So we initialize our time, and then we write our loop just as before. So we initialize t to the value a. When it's less than b, we continue to step at a pace of dt. And then because it's dynamic, it can be helpful to have log messages within the loop to see how it's evolving. Make sure you can verify that it's computing sane values and that you haven't introduced some bug. So we'll give the ordinals x is always the first one, y is always the second one. The way we've defined the vector, it is the second one. Or in the 1 slot. In the 2 slot is theta, and then speed is that last item in the vector. Okay. So then our derivative given by the output of f of t as defined above, our sample function. It's actually sampling the derivative, x prime. And so our implicit function, the value at time t, is given by an evolution of states. So there's the value at the previous state, and then it moved at a pace dx dt for a step size of dt. Okay. So the previous position plus the rate of change times time to get the new position. Okay. And then that is actually copied everywhere. So that same simple formula, that evolution formula, current plus the rate of change times time, is applied in every place. So now, we'll print out the final time. And it's really the same thing as up here. So let's run it. And we can see the evolution, how fast it was moving. We could do some additional work to find out what the actual drag was at any given moment. But we can see that how the system evolves with respect to time. So it's moving horizontally pretty constantly. And it goes up, and then it comes back down. Okay, so that's numerical integration. It can range from really, really simple to a lifesaver. Right? So I wouldn't want to compute this by hand. And so you can imagine how some of these dynamic problems seemed totally out of reach whenever you needed some closed form solution. But with differential equations, like as you study it, the equations are right there. And so if you learn how to manage it, and this is really it. This is the formula that you use in graduate school differential equations, where you just simplify it to some implicit function and some function where you're dealing with all of the derivatives, and then you can compute this time-evolved function based on some initial state or some boundary conditions, and then the definitions of all of these derivatives. So that's it. I mean, that's basically the trick that you would use to do numerical integration. Some programs like MATLAB or some platforms like MATLAB will have built-in numerical integrators, and so you'll want to learn how to work with those. But again, it's not something, just like whenever we're talking about sine and cosine. If you understand what's happening and how it all works, then you can write your own. But it can be really nice to rely on a set of libraries that'll help you get it accomplished. Okay, we will discuss, what did I say the third thing was? AVL trees. AVL trees and probably heaps and stuff next time. I want to make sure that we're still coding as we go along, and that we never stop discussing proofs the rest of the way as well. Right? So I will make sure to get you at least one more homework assignment before the end of the semester, but the vast majority of you are doing extremely well. So, okay, I will speak to you all on Thursday.